In this video, we're going to learn about a few new useful Opamp circuits and analyze them with our golden rules. So the first circuit, and I'm not going to tell you the names ahead of time because I'm going to get to the name at the end as a surprise treat. I don't know. Okay, so our first circuit looks like this. We have an input voltage, and we have output voltage over there, and we have two resistors in between here. So this resistor we will call R2, this resistor we will call R1. We're going to actually keep this general in terms of these resistor values, and just for the sake of analysis, we're going to call this point A, just so it's easy to refer to. Okay, so our Opamp golden rules tell us that these two voltages are going to be the same. So that is VA wants to be equal to Vin. And there's no current in or out at point A, which means this we can now treat as a nice voltage divider on its own. Right, so that is going to look like this. V out, R2, Vin, R1, 0, assuming that it is able to keep VA equal to Vin. Okay, so we could figure out the relationship between Vin and V out without even writing down a current. We could just look at this just as a voltage divider, right? So Vin is going to equal R1 over the total resistance times V out. Which of course means that if we solve then for V out in terms of this, we get V out equals R1 plus R2 over R1 times Vin, which we can also write as 1 plus R2 over R1 times Vin. Okay, so that was our whole analysis of this voltage divider circuit, and therefore our analysis of the relationship between Vin and V out. So note now that Vin and V out are still just directly proportional to each other, like in our last circuit we looked at. So V out is equal to something times Vin. This is, again, our amplifier gain. In the case of the inverting amplifier, this value was negative. For this circuit, remember, R1 and R2 are always going to be positive. Resistors are always positive. And so whatever values we plug in here, this gain is also always going to be positive. So rather than Vin and V out having an inverse relationship, where if one goes up, the other goes down, these two have a not inverse relationship. This is the non-inverting amplifier. It seems silly you have to say non-inverting rather than regular amplifier, but that's what it's called. So the differences between the non-inverting amplifier and the inverting amplifier. One, like I just said, when the input goes up, the output goes up. That may or may not matter depending on what you're doing. Another important difference is that for the inverting amplifier, our input was connected to our feedback loop and to these resistors, which means even though the Opamp inputs didn't take current from the input, the resistors do. So you do need some current in the input of the inverting amplifier in order to make it work. Here, our input goes directly to the input of the Opamp where no current is supposed to flow. So this setup will require much, much less current from the input voltage source, whatever it is, because of that. So that can be an advantage. It can be a disadvantage because that can make this sensitive to certain kinds of noise also. But that is at least a difference to be aware of. Okay, great. The next Opamp circuit I wanted to show you is still very much related to these last these previous ones we've looked at. So here, and this is the simplest op-amp circuit, I think, but far from the least useful. So here we have our op-amp. We have our input voltage going into the inverting input. We have feedback between the inverting, our voltage input goes to the non-inverting input. We have feedback at the inverting input and to the output. So there are no resistors here. So we can kind of think about this like the non-inverting input, where R2, the feedback resistor, is set to 0 ohms, and R1, which is the resistor to ground, is set to like an infinite number of ohms. If you plug those into our gain equation, this gives us a gain of 1. Is there another way we could see this gain of 1? Well, yeah, our golden rules, right? Our op-amp wants to make these two voltages the same, and those two voltages are Vin, and this voltage is just equal to V out. So our golden rule tells us that Vin is equal to V out. Okay, so I have an op-amp circuit. It costs me, however many dollars to build, and my output voltage is the same as my input voltage. Like, what the heck have I accomplished here? Why is this useful, right? A gain of 1 means that nothing has happened. Yes, except it turns out this is very, very useful if your input is coming from a source that cannot supply very much current. So a source with a high series resistance. So for example, if we had something that looked like this, some signal here that has a source resistance of 1 mega ohm, so something really big. So this whole thing is our voltage source, right? And we try to connect this to a load. Maybe this is a signal coming from some sensor, or a signal coming from your computer that can't output very much power, but you still need to be able to do something with it, right? And your load is 100 ohms. You need to run a motor or turn a light on when this happens, or something, right? If you try to do this, whatever output you have here, if this is like, let's say 10 volts, you have, 10 volts trying to be supplied by your circuit, and 10 volts you would measure if there was no load attached here. But when you have 100 ohms in series with your 1 mega ohm, that's, a factor of 10 to the fourth. So you're going to measure, like, at this point, instead of measuring 10 volts, you're going to measure like 1 millivolt or something like that. 1 millivolt. So that is bad, right? We would like to be able to send this 10 volt signal, without losing 99.9% of it or whatever. Okay, so what we can do is we can put this circuit in between these two, and then connect our 100 ohm load to this. And now, remember, no current passes into the inputs of the op-amp. So there's no current that passes here, which means there's no drop across this resistor, which means this is still 10 volts, which means this is still 10 volts, which means we get all of our 10 volts to our load. So that's because, our op-amp is getting power from somewhere else, but it is going to perfectly reproduce whatever's happening at this input. And that's that's important. And that's, it's still constrained, of course, by the limitations of the op-amp in terms of how much voltage and how much current, but it's almost certainly going to be able to do a much, much better job than anything with a high series resistance. Okay, so this is called a voltage follower. And, we talked about transistor voltage followers a couple weeks ago. So this is the same idea, except it's not going to have that 0.7 volt drop. And if we have the right power supply, it can go positive and negative. This is a much, much better voltage follower than a single transistor. This is also called a buffer. The idea there is that if you have some signal, you can send the signal into this buffer, and it it holds and preserves it, not in the memory storage sort of way, but in the you know, it is whatever's over here is not going to be affected by whatever is drawing the current over here. Yeah, that's what it means by buffer, and like acts to separate those two. All right, cool. The last op-amp circuit is the following. All right, so here we have a circuit with 3 different voltage inputs, V1, V2, and V3. These each go through a resistor, R1, R2, and R3, and then are connected to the inverting input, which has a feedback resistor of value R0 and is connected to the output. Okay, so again, quick golden rules. So the op-amp is going to try to keep these points the same, which means it's going to try to make this point equal to 0. And that means that we can figure out what the current is through each of these pieces, right? So if we have a current here, I1, I2, I3, I1 is equal to, you know, I equals V over R, and because this, you know, remember, this is all 0 volts over here. So the voltage difference is V1. I2 equals V2 over R2, I3 equals V3 over R3. So this is, you know, this is easy to figure out. And these currents all meet up at this node, and so the current into this node has to be I1 plus I2 plus I3. The current out of this node has to be the current through that resistor, right? So we have 3 currents going in, 1 current going out. I will call that I0 just for symmetry's sake, I guess. So I1 plus I2 plus I3 equals this I0. And I0 we know in terms of this voltage and this resistance. So that is 0 minus V out, the voltage difference across that resistor, over R0. V over R, this is our current I0 through this resistor. So putting all these into the same equation, I get V1 over R1 plus V2 over R2 plus V3 over R3 is equal to minus V out over R0. And we can now solve for V out. So V out is equal to minus R naught times 1 over R1 V1 plus 1 over R2 V2 plus 1 over R3 V3. So our output voltage is proportional to some combination of the input voltages, each multiplied by some number and then added together. So this is called a summing circuit. You can imagine if we picked the right resistor values. Well, let's just say if all of the resistor values are 1 ohm, all of these R0, R1, R2, R3, all of those just go away, and we're left with V out equals minus V1 plus V2 plus V3. So that clearly is you know, the output is the sum of the inputs times a factor of -1. We can weight these voltages differently, so maybe one of them is more important than the other, so you change the resistor value so it gets, you know, included more, kind of a weighted average or a weighted sum, you could kind of think of that as. Anyway, so summing circuits can be useful for combining signals into one signal, and there are reasons to do that in, you know, audio systems if you're adding adding sounds together, or in scientific systems if you're combining information from different sensors or that sort of thing as well. Anyway, so conclusion of all of this, our op-amp golden rules make it very easy to analyze complicated circuits basically just with Ohm's law, right? That's other than the golden rules, Ohm's law, and a little tiny bit of Kirchhoff current law here. That's the only thing we've had to use, and we've gotten some really some neat results for some pretty complicated op-amp circuits.